Okay, a bit of review. What are atoms? Now, in ninth grade, you probably learned about atoms already, and hopefully, this picture that you see right here looks familiar. This diagram, actually, when it was first invented or drawn up by this guy, Niels Bohr, back in about the 1920s, it was a huge breakthrough at the time, and even though it was outdated very shortly after it was drawn, you still see this diagram all over the place in reference to atoms, atomic structure, and things like this, just because it was such a huge breakthrough and it made a lot of sense. And as we go through this unit and subsequent units, we'll be learning about atomic structure and how the periodic table is laid out according to that, and all kinds of things like that too as well. But hopefully, what you're looking at here is something that you already know a bit about. Like, for example, the thing in the middle is the nucleus, which you had a attendance quiz about that. The nucleus, which is in the center of the atom, and it contains protons and neutrons. Protons are positive, neutrons are neutral. Those two particles are about the same size, and surrounding them then are these electrons that fly around, and sometimes we say they fly around the nucleus like planets around the sun. And electrons are negatively charged. Sometimes we write E with a minus sign to indicate that. Now, as we get deeper and deeper into this, we'll learn that this model is actually kind of outdated, and it's a lot more complicated than it is suggesting. And this model just suggests that this electron flies around like planets fly around the sun, and then there's another one, and so on, going around it like this. As it turns out, the electrons are behaving a little bit more as though they were just energy rather than a particle flying around. And then they do things that energy waves do, like light that has wavelengths and amplitudes and stuff like that. But that's a bit further down the road. For now, the model is pretty good at illustrating a number of things about atoms, having the nucleus in the middle and having electrons surrounding it somehow. And it was a good model and a huge breakthrough at the time. Now, if we look at the history of atomic models and trying to figure out this kind of information, we'd really have to go all the way back to the time of the Greeks in centuries BC. And the Greeks were probably the first recorded evidence of people thinking that atoms might exist. And in fact, the word atomos is in Greek means cannot divide, and the word atom is derived from that. So even early on, people believed that there's a very fundamental particle that everything is made of, even though they knew, even at that time, that you wouldn't be able to see these things because they're so incredibly small. But they did believe that there were different kinds of atoms, and they had come up with these concept of the different elements, different Greek elements. And this is not far from what we even know today. Rather than the elements that we know of today, this is more in line of like the states of matter. For example, Earth represented anything that was like solid, all right, like solid. And anything that is solid then is made out of Earth atoms, basically. And then you've got water, and that kind of corresponds to anything that's a liquid for the most part. And water is a very unique material that's around us, all around us, oceans, lakes, rivers, things like that as well. And then there's air, and we know the concept of air. And then there's air atoms, and this is what we would probably consider to be like gas. And then we have a solid, liquid, gas, and then there's also plasma, which is what fire is. So they were not really too far off in their thinking, even back at those times there. And they thought then you could have solid particles, gas particles, liquid particles. They could come together, and then everything that we know of is kind of a combination somehow of all these things put together. And that kind of makes sense. Solid things like our bodies require liquids, and we are warm, therefore we got plasma in us, and we have to breathe air. So, even our human bodies kind of incorporate all these little things in some way, shape, or form. So they were really onto something there, but it took centuries for us to all get to the point where we know that atoms have a nucleus and electrons and protons and all that kind of thing like that too as well. So one of your first assignments in this business then is to create a timeline of various scientists and discoveries that were made leading up to the current model of atomic structure. Okay, let's take a look at a piece of the periodic table. Now, most of you are probably familiar with the periodic table, and each element on the periodic table has its own box, and inside of that box there's various information. Now, there's different kinds of periodic tables, of course, that have different information, and it might be laid out differently too as well on there. So here's an example of the element carbon, Now, the first piece of info that we might look at is a big number, in this case 6. That's the atomic number, which represents the number of protons in the nucleus of that particular atom. So any atom that contains 6 protons in its nucleus is going to be a carbon atom. That's the distinguishing characteristic of a carbon atom, that it has 6 protons in its nucleus and its atomic number is 1. Now, the simplest element is hydrogen, and that has just 1 proton, and then there's helium, and then lithium with 3 protons, and so on. And as you go across the periodic table, you got rows, you've got columns and stuff, and each time we add a new proton to the nucleus, we create a new element. So that's what makes one element different from another, is its atomic number, or the number of protons that are in the nucleus. Another piece of information that is in each box is what's called the atomic mass. That would be the mass of a mole of atoms measured in grams. Now, how many things are in a mole? We talked about before, 6.02 times 10 to the 23rd. So if you had 6.02 times 10 to the 23rd atoms, in this case you would have 12.01 grams for carbon. Now, 12 grams of carbon, that would be small enough to fit as a little lump in, like a chunk of charcoal is mostly carbon, and it might be 12 grams. You can fit it right in your hand. And that means that you would be holding billions and billions of carbon atoms in that chunk of carbon. All right, so that's what that number represents. All right, the atomic mass. It's the mass of 1 mole. Now, we sometimes also call it the molar mass, or sometimes even goes by the name atomic weight. All right, but it's basically the same thing. It's how many grams there are in 1 mole of that particular element, the atomic mass. Now, if you look at your periodic table, right in the middle, there's sort of a key that tells you what each piece of information in the chart is. Next, then, we have the mass number. That would be the number of protons and neutrons added together. So in the nucleus, how many particles are in the nucleus? The mass number. It's the number of protons plus neutrons added together. Now, from the periodic table, how would you decipher that? All right, you could decipher it from the atomic mass somehow, because that's the mass of the average of all the known isotopes of that element. So before we know exactly what a mass number is, let's talk about what an isotope is. Isotopes are atoms of an element with different numbers of neutrons. So in the nucleus of a carbon atom, there has to be 6 protons. That's why it's a carbon atom. But the number of neutrons that are there could be different from atom to atom. So when you have different numbers of neutrons in the nucleus, then you have a different isotope of that element. All right. For example, in carbon, you might have 6 protons. But you might also have 6 neutrons. All right. Therefore, the mass number for this particular version is going to be 12. It has 6 protons and 6 neutrons, so the mass number is 12. Now, you could also have a a carbon atom that has 6 protons but has 8 neutrons as well, and in which case that's going to add up to a mass number of 14. All right, so the mass number is what distinguishes one isotope from another isotope, is how many neutrons it has. Now, to be called a carbon atom, you must have 6 protons, but you could have different isotopes of carbon having different numbers of neutrons, and therefore the mass number is different. So you could also say that an isotope is a member of an element with different mass numbers too as well. Now, to distinguish from one isotope to another, we could use what's called nuclear notation. All right, what is this? What is this? If I wrote the element symbol C, and then out in front of it I wrote a number 6 sort of down below and a number 12 up above, these numbers represent two things. The number below is the atomic number, the number of protons, 6, and that's why it's carbon. And the top number is the mass number, the protons and neutrons added together. So this particular notation here, element with a number, 2 numbers out in front of it, is what we'll call nuclear notation. It tells us something about the isotope nature of it. To be carbon, it would have to have a 6 down below, but it could also be a different version of carbon, having 6 protons, but in this case 8 neutrons, and therefore a mass number of 14. So 6 plus 8 adds up to 14. All right, we call this carbon 14, and we could also write that out as carbon dash 14, and the other one could be then carbon dash 12. All right, we sometimes also just write it as C14 or C12, like that. Just another way to write it. It's just a way to denote different isotopes. Now, some of these isotopes of elements are actually radioactive, and that is the case with carbon 14. It happens to be radioactive. Now, if you were to go out into the environment and just say, grab a sample of carbon, and you could do that in your own person. Your body's made mostly of carbon. Some of it is carbon 12, actually most of it is probably carbon 12, and a small amount of carbon 14. And carbon 14 is radioactive, and we can use that fact to find out how old things are, like dinosaur bones. All right, you ever wonder how can you dig up a dinosaur bone and figure out that that thing's 10,000 years old? All right, the way we do it is we look at how much carbon 14 is in the bone, because once the animal died, it doesn't make any new carbon, or it doesn't consume any new carbon. So however much carbon 14 is there when it died slowly disintegrates over time, and it takes a very long time for it to disintegrate. So we look inside the bone and see how much carbon 14 is still there, and then we can figure out how long ago it was that that animal died. All right, it's called carbon dating, and it uses radioactivity, something we'll learn a bit more down the road. Now, to be called carbon, you must have 6 protons. How many neutrons, though, could vary from carbon atom to carbon atom, but what we find in nature is that there's not an infinite number of possible isotopes. There's only certain isotopes that we actually observe. And if you start adding neutrons to a nucleus, at some point the nucleus becomes unstable and it just disintegrates, and it just falls apart and turns into something else called radioactivity or transmutation, something we'll talk about a little bit more later. So the known isotopes of carbon are just these 2 right here. All right, other elements have more than 2 isotopes. It kind of depends on the element and the size of the nucleus. All right, so that's a little bit of review. You maybe didn't talk a bit about isotopes last year, but you certainly did talk about atomic number and mass number and stuff like that, and the periodic table too as well. Other information in the box, of course, we got the symbol and we got the name, and then this little indicator here tells us that it's a solid, normally at room temperature. And then the plus and minus 4 here is something about gaining and losing electrons, and we'll learn about that business a little bit further down the road too as well. All right, let's take a look at this chart. This chart has under the column for isotope chromium with a number behind it. Remember that that number written behind it like that is the mass number. It's the number of protons and neutrons added together. And since all of them are chromium, then how many protons do they have? Well, that is determined by the atomic number. The atomic number. So since it is chromium, the atomic number is 24. Therefore, all of these will have 24 protons. All of them will have 24 protons. That's why they're called chromium. All right, now what's chromium? Chromium is an element. It's kind of prevalent. We use it in a lot of places. Anytime you see something that's really shiny, like think of like the legs on your desk when you're at school. They're nice and shiny metal looking thing, and they don't get rusty and corrode. That's probably got chromium in it. All right, we mix it with other metals to keep stuff from getting rusty and staying nice and shiny all the time. Chromium. All right, you might also find it in, for example, in a toaster. If you ever looked inside of a toaster, that little thing that gets red hot in there probably contains some chromium in it. It's probably chromium nickel mixture is what it is inside there. So we use chromium in lots of different places too as well. Now, how many neutrons does it have? Well, if the atomic number is 24 and the protons and neutrons added together must come up to be 50, that tells us that there must be 26 neutrons here. 24 plus 26 adds up to 50, the mass number of that particular isotope. Now, in the case of chromium-52, then it must have 28 neutrons. And chromium-53 has 29 neutrons, and chromium-54 has 30 neutrons. All right, now, notice that we had 50, 52, 53, 54, what about 51 in between? Well, these are the known isotopes for chromium. All right, if we went out and we scooped up some chromium out of the environment somewhere, which would probably be sealed up in rocks and things like that, we would find that there's 4 different known isotopes of chromium. All right, now the mass numbers are these. If I were to somehow, but each one of these might occur in a different percentage in nature. And in fact, we could figure out what the most common isotope of these is by looking at the atomic mass. All right, because the atomic mass or the atomic weight, this is an average of all the known isotopes of it. And that average is fairly close to 52. All right, 51. If I rounded it, say, to a whole number, I would get 52. What that tells me is that chromium-52 is the most common isotope for chromium. And since it's a little bit below 52, then there's a little bit more of chromium-50 kind of bringing the average down a little bit. Chromium-53 and 54 would bring the average up. So there must be, the most abundant would be chromium-52, followed by chromium-50, if that's the only other isotope below 52, bringing the average a little bit below 52. So to find the most common isotope, I would take that atomic mass or atomic weight and round it to a whole number, and that'll tell me the mass number of the most common isotope. All right, the reason why this is not a whole number is because we're taking an average. We call it a weighted average, which we'll learn about that a little bit more later too. All right, now a weighted average is different than a regular average in the fact that if I took the average of 50, 52, 53, 54, I would just add them all up, divide by 4. All right, but a weighted average uses the fact that you don't just have one of each of them. You might have a whole lot more of 52 than you do of 51 and 52 and so on. And you have to do what's called a weighted average. All right, we will look at that a little bit more later. All right, let's do one more thing before we end here. All right, we got a little piece of the periodic table here, and we have a chart to fill out. All right, let's see if we can fill out this chart for the element sulfur. All right, for the element sulfur. All right, so the symbol for sulfur, here it is right here, is that box, sulfur. Its symbol is 6S, and its atomic number is 16. Atomic number 16, element number 16. All right, the atomic mass, well, that would be that number 32.07. 32.07. All right, remember, that's an average of all the known isotopes, which is why it's not a whole number. But if I rounded it to a whole number, 32.07 rounded to a whole number would give me just flat out 32. That's going to be the mass number, at least of the most common isotope. All right, the most common isotope is that. There must be a little bit of, sulfur 33 or 34 or something, bringing the average up just slightly. All right, number of protons, well, that is exactly the same thing as an atomic number. All right, atomic number. Now, remember that a mass number is the number of protons and neutrons added together. Therefore, how many neutrons are there? There would have to be 16 neutrons. So 16 plus 16 adds up to 32. Adds up to 32, the mass number. All right, so protons, neutrons. Now, that's for the most common isotope anyway. It would have 16 neutrons. Now, there might be other isotopes that have different number of neutrons, but the most common one. Didn't really say that in the chart, but we'll have to infer that. All right, number of electrons. Now, the number of electrons for now, we are always going to say is exactly the same as the number of protons. All right, now, some elements like to gain and lose electrons, in which case they turn into what's called an ion, and that would be when you don't have the same number of protons as electrons. All right, so for now, we're just going to say the number of protons and electrons are always going to be the same. And there are reasons why and when atoms gain and lose electrons is something we'll learn about a little bit more later. That's why chemical reactions happen and compounds are formed and stuff like that when atoms like to gain and lose electrons or sometimes share electrons. But that's a little bit further down the road too as well. All right, so just by looking at the periodic table, we can decipher all kinds of information like is in this chart here as well. All right, we got the element name, we got the symbol, we got the atomic number, which tells us the protons, we got the atomic weight, which could tell us something about the mass number of the most common isotope anyway, and the number -2 tells us that sulfur likes to gain 2 electrons. Electrons are negative, therefore -2. All right, but that's a piece for further down the road. All right, so that's a quick little review of some stuff that hopefully you learned already in 9th grade, but we will use the periodic table a whole lot more later. All right, other stuff that you see on the chart here in the middle of your periodic table, there's a key that tells you what this information means. For example, these symbols right here all indicate that these things are a gas at room temperature. All right, these things here are solids. These things here are solids. All right, the numbers down below tell you about gaining and losing electrons. All right, there's also a little thing right here that tells us that these things are what's called a diatomic gas. All right, but that business is business that we'll take up a little bit further down the road.